The stream of people has started to subside. People coming in. So we'll start. This is Peter Seibel, who has written an excellent book called Practical Common Lisp about Lisp. And today he's talking about how choice of programming language influences the way you think about writing your code, or how your architecture ends up looking. I guess we'll just start.
Okay, so this mic is on. Yep. Okay, so this is a version of a talk that I gave to a SIG in the West Coast, where I'm from, the software architecture and modeling SIG, and so they were all into the whole patterns thing and stuff. So there'll be a little bit of stuff about that, but I suspect that, and I got some feedback from even those guys, that the thing they were really interested in was actually hearing about the sort of language differences, Common Lisp versus the world. And so I'll talk a little bit about sort of the theory of architecture very briefly, because that's a bunch of hand-wavy stuff. And then we'll look at a few features of what I think of as the key features of Common Lisp and compare them, in some cases quite specifically, like here's how something gets done in Java, and demonstrate how patterns are used. So I'll do a little language comparison, a couple key features. Obviously I'm not going to cover all of Common Lisp. It took me 2 years to write the book. It's 500 pages long. You want to learn the whole deal, read that, and there's still stuff that's not covered. Though part of the goal of this book is, if you are, as I assume almost everybody in this room is, an expert programmer in some other language, and some of you may be expert Lisp programmers as well, but if you're not an expert Lisp programmer but you know how to program, this book should be the shortest path from here to understanding what Common Lisp is about, and that was really my goal. I wrote it with all of my friends that I used to work with at WebLogic in mind, who are all super smart programmers, who all thought I was crazy to think Lisp was a great language, and so I was constantly trying to imagine what they would be saying to me. So that's the end of my plug for my book. So as I just mentioned, working backwards, before I wrote the book, I was hacking Java at a little startup in San Francisco called Kanemea, where we were building a big transactional messaging system in Java that was founded by one of the WebLogic founders who had left WebLogic, where I had worked with him working on the WebLogic application server. I was the early employee there. Prior to that, I was a hardcore Perl hacker at web shops like Organic Online. And before that, I was a would-be journalist and English major. So that was my circuitous road to Lisp. But I started, my dad was, as I mentioned in the introduction to my book, I'm one of the few second-generation Lisp programmers in the world. My dad did Lisp in the 80s, when it was the last time it was big, right? The next time is coming up right now. So I learned in my father's knee that Lisp was really the bee's knees, and I sort of spent my career winding my way back. So, if I'm going to talk about how language affects architecture, I'm going to talk a little bit about what architecture is. I'm going to, y'all, if you write software, have some notion of what it is. I'm just going to frame it very briefly. Obviously the reason for doing architecture is to keep our systems intellectually manageable and to some extent to coordinate group efforts. One of the ideas about what software architecture really is that I find really interesting is from Peter Nahr, who's the N in BNF. He wrote an essay which was reprinted in one of the Agile programming books about how what you do when you develop software is you develop a theory, which actually has a sort of special meaning, a theory of how the program works. And if you have the theory of how a program works, then not only can you, well, basically, if you don't have a theory of how the program works, you can't do things like modify it or find bugs in it or whatever, explain how the parts of the program relate to parts of the world that it's supposed to be emulating or interacting with or whatever. And he has a sort of interesting take on what this is all about, that the essence of getting a theory of a program is sort of a AI complete problem. The only way that you can really understand how a piece of software works is actually to have either written it or to have worked very closely with the people who did write it and who passed the theory on to you. You can't take a piece of programming, the text of a program, and back out the theory without an incredible, an amount of work that's equivalent to just writing the thing. And the reason that that's interesting to me as relates to Lisp is because obviously, while I think that's probably true of all languages, obviously some languages, as they get higher level, it's easier to encode more of your knowledge about the theory that underlies a program into the program itself. Obviously, if we have, the machine code that your compiler gave you, it would be a lot harder to back out what the heck the program is doing than if you had the source code in any high-level language. And from there, we can extrapolate, well, maybe even more expressive languages would make the theory of a program more accessible to either newcomers to the program or to you yourself, a week later, a month later, a year later. The other thing about, there's nothing here, I know.
Okay, you keep hitting buttons.
Yeah, it's cue cards. I'll talk about the presentation software later. I'm a believer in the Tuftian PowerPoint is the root of all evil theory, but there will actually be a few slides up here later. So another approach that you're probably all familiar with to how the heck do we do software architecture is the pattern movement. Christopher Alexander, building architect, had this whole theory about patterns. Other building architects completely blew him off. Software people said, wow, this is really cool, we can apply this. This is exactly how we build software. And thus the pattern movement was born. The thing that's interesting about patterns, again, as relates to choice of programming language, is to what extent do the patterns and beyond individual patterns, the pattern language, which is sort of the sum total of everything you know about how to put stuff together, whether it's buildings or software, how is that affected by your language? Would you use the same pattern language regardless of your implementation language, or does your implementation language essentially set the stage for what possible pattern language you could be using? So to understand that, we have to think about, well, what are patterns really? And the way Alexander talks about them is individual patterns are designed to resolve specific forces. And by forces, he means things that are, I guess at the base case, there's just sort of this stuff from physics, right? You build the building wrong, it falls down. But he was particularly interested in things, the forces that are either inherent in human beings, like one of the examples is people like light, and therefore people are more comfortable in well-lit rooms, and he has a pattern which is light on two sides. A room that's got windows on two sides is more likely to be well-lit more of the time, and therefore will just be a more comfortable room to be in. And people might not identify that's why, but they will gravitate to rooms like that. And if you actually look at the rooms in your house that you like spending time in, you'll probably discover that that pattern and many others are present. There's also cultural things. He talks in one of his books, The Timeless Way of Building, about building houses in Peru, where culturally women were expected to stay in the home and weren't sort of allowed to go out and participate in the life on the street. So they had to build houses where there would be an alcove sort of half in and half outside of the house where women could stand and be in the house yet see the street. And so obviously that's not universal to all human societies, but in that culture, it solved the problem, these forces that if you didn't have that, either women would be forced to just hide in the house and be completely disconnected from the world, or they would have to go out into the street and sort of suffer the mental anguish of breaking the mold of society. Now, whether that would be good for the society as a whole is another question, but that's the kind of cultural forces. So in software, we have different forces to contend with. The physics of software are just math. Big O, complexity, stuff like that. If you build it wrong, it will either fall down or never finish, or all of the sort of basic stuff. But analogous to the inherent nature of human beings and the nature of cultural influences in software, patterns are designed for, so building patterns are designed for people who live in buildings. Software patterns are for people who live in software, namely all of us, people who write software. The fact that software is then used by users, the patterns don't matter, right? The user is just running a binary, so the patterns are long gone at that point. But the patterns are for the people who live in the software day in and day out and have to deal with it, have to modify it, have to, are affected, are depressed when they're presented with a big mass of code that nobody can understand, and feel good and happy when you're working on code that you wrote. It's beautiful, it's elegant, you understand how it all fits together. So there's built-in limits, the 7+2 rule, you just can't remember that, plus or minus 2. You can't remember that many things, so if your software architecture is predicated on remembering 20 things in your mind, it's probably going to fall apart. And also, we obviously have cultural biases, and this is where Lisp sometimes runs into trouble. People go through great pain in grammar school and junior high learning the stupid precedence rules for infix notation and are now convinced that infix notation is the one true way to notate arithmetic expressions. And then Lisp comes along with prefix notation and they say, that's just weird, that's stupid, infix is the natural way to do this. So language wars are often fought on the grounds of what's natural, and people have a hard time keeping track of what's natural and what's just repressed pain of they've already learned. All right, so, and then patterns, again, in building or software, are all put together into a pattern language, and that's really what Alexander was looking for, was sort of a generative language where you have a number of patterns where each pattern you apply resolves certain forces, but the pattern itself causes new forces to come into existence that you then have to resolve, and so you need another pattern in your language that can solve that. And if you have sort of a set of pattern whose transitive closure can resolve all of the forces and leave you with a coherent whole, that's a good pattern language. And then there's a whole nother level for Alexander of, you want patterns and pattern languages, and then the buildings or software that you create needs to have the quality without a name, which is a whole philosophical hand-waving thing that you've probably scratched your head about if you've read any of the pattern literature. So that's patterns. So how do patterns relate to languages? Well, I would suggest that if you think about it at all, the universe that we live in when we write software is itself built out of software, right? Unless you're writing microcode for a new CPU, there's already many layers of software in place before you come into work. And that software creates the universe in which you live and creates the set of forces, the base set of forces which you have to contend with, and as you add software to the system, you're just changing those forces. So, you could start from bare metal and build all of your software up from machine code. And if you were smart, what would you do? You would write a language, and that language would now create a new universe in which to work. So, and then most languages provide some facility for then creating new languages, or at least new abstractions within the existing language. It doesn't seem likely that a single pattern language would apply equally well whether you were starting from bare metal or starting from any high-level language, and then different high-level languages, if they're different, are going to call for different patterns. Okay, so that's sort of how this all works. And the Gang of Four, the design patterns books, they pretty much say this. In page 4, they say, our patterns assume Smalltalk C++ level language features, and that choice determines what can and cannot be implemented easily. If we assume procedural languages, we might have included design patterns called inheritance, encapsulation, and polymorphism. Similarly, they sort of do my work for me. Similarly, some of our patterns are supported directly by less common object-oriented languages. Class, which is Common Lisp's object system, has multi-methods, for example, which lessen the need for a pattern such as visitor. And so that's, they sort of say it right there. Okay. Well, okay, and then one other little grenade to toss in here. Who here has heard of the Sapir-Whorf? Yeah, okay, that's good. Who here, I should have asked this at the beginning. So who here has used Lisp in any kind of serious way? Yeah, all the same people who know about Sapir-Whorf. Sapir-Whorf is a hypothesis from linguistics or anthropology or whatever. Basically, these folks noticed that human natural languages differ, obviously, and theorized that how you understand the world is constrained by your native language. and they observed that, I mean, the sort of famous example, which I think was later debunked, was the idea that the Inuit have 28 billion words for snow, and they have thus this much finer sense of different kinds of snow. So that particular example turned out to not be so true. There were other examples that have actually been verified, like languages that don't have words for certain shades of colors. People can recognize the colors perfectly fine, but when asked to remember later what color certain objects they were shown are, their ability to remember that is in fact infected by the colors that their language supports.
Is it still believed to be true by orthodox linguistics?
Yeah, and so there's two flavors of, so Sapir-Whorf is sometimes called linguistic determinism, and there's two flavors. There's strong linguistic determinism, which is basically you can't think anything that you can't say in your language. And then there's weak linguistic determinism, which is basically your language affects how you think. Strong linguistic determinism is pretty, like, the most, well, obvious and compelling argument against strong linguistic determinism is we can translate between languages. If it were literally true that you couldn't think anything that wasn't encodable in your language, you could never translate from one language to another. Which is actually interesting then when we go to computer languages, because of course Turing completeness tells us that all languages are absolutely translatable. Anything you can express in one programming language can be expressed in another. So there is no, you could argue that in fact human languages can't be translated. You can only approximate the meaning between French and English, and that there is a difference. But computer languages, we know it's math. It's not true.
Even the weak version is generally dismissed. That it has nothing to do with the language. That it has to do with practice thinking about it. For example, if I don't throw a baseball, I'm not a very good baseball thrower. So simply practice with the concepts has nothing to do with the language.
Right, and I suppose that someone who wanted to defend even the weak version of linguistic determinism would say, well, yeah, but that may be the mechanism, right? You practice thinking a certain way by using, but that's not right. It's I'm just going by the wiki. They say that the Wikipedia. There's some respect for the weak version left. So anyway, and so computer scientists have noted this analogy between natural language and computer language. Alan Perlis, professor at Yale, said a language that doesn't affect the way you think about programming is not worth knowing. You probably all heard about Eric Raymond saying, well, you should learn Lisp just because it will change the way you think. And that's why Lispers have always heard of this, because Lisp is always held up as an example of a language you should learn because it will change the way you think. The interesting question to me is, so that's great, it'll change the way you think, but do you have to use it, right? If Paul Graham, I don't know, you all heard of Paul Graham, I assume. If you heard about the Blub paradox, so Blub is this notional intermediately powerful programming language, and his theory is that if you only speak Blub, you look at less powerful languages and you can see that they're less powerful because you see what they lack relative to Blub. But if you look at more powerful languages, they just look weird because you can't think of the features that those other languages support, and so it just looks like Blub plus a bunch of gunk that makes no sense. But if you sort of take the Raymondian hypothesis that you should learn Lisp because it will change the way you think, that sort of implies that you could learn to think in omega. If omega is the ultimately powerful language at the top of the lattice of all, where languages are ordered by power, you could learn to think in omega and then work in Blub and get, all the benefits, or 99% of the benefits. And that may be the case, and I'm going to give a demonstration now of why that's probably not, and that's basically the reason not is provided concisely by another Alan Perlis quote, which is, "Beware of the Turing tar pit, in which everything is possible, but nothing of interest is easy," right? Like, yes, you could take Omega, you could take a raw CPU, and you could write all of the code. You could just start by writing a compiler for Omega, and then write the rest of your stuff in Omega, but that's really not how you're going to get software done in this, millennium. So it does, I think, matter what languages you actually use, not just how you think about coding. So So Lisp is my favorite. I don't think it's necessarily Omega. There's, and the Haskellers and the MLers would say, well, from where we sit, Common Lisp looks like Blub, and you just don't understand, the brilliance of the strong inferred typing and all of that. And they may be right. Of course, Common Lispers look at Haskell and say, well, Haskell's really a Blub because you guys don't have macros, and so it may be the case that there is no Omega, or that Common Lisp and Haskell are on different branches of the lattice, and someone's going to find a way to unify them and a few other good ideas and produce Omega. So, but smart folks have noted this. Dijkstra, sort of this is Sapir-Whorf right here. Lisp has assisted a number of our most gifted fellow humans in thinking previously impossible thoughts. And sort of to echo the patterns notion, Alan Kay, another Turing Award winner, inventor of Smalltalk, Lisp isn't a language, it's a building material. And I'll sort of show how that works. Okay, so the first thing I want to talk about is to compare. I'm going to do a little comparison. I assume everyone here has at least a reading knowledge of Java, whatever, it'll make sense. Java's the, because I'm going to show how a pattern, the visitor pattern, which who here has heard of the visitor pattern? Okay, is implemented in Java typically, and what problem it's aimed to solve. And then I'll show how that pattern sort of doesn't exist or is not needed in Common Lisp, because Common Lisp essentially has those forces pre-resolved by virtue of the language feature. And this sort of shows the Turing tar pit. Yes, you can implement this in Java, and I'll show you the reams of code you have to do that, or you can just use the feature of multiple dispatch in Common Lisp, and it's just there. So we'll take a concrete look at how that works out. So before I start, I just want to point out, to me, the essence of the visitor pattern is the double dispatch, right? When the visitor pattern is presented, it's usually in terms of walking a tree, like you have a tree of, abstract syntax tree, the tree of nodes, or you have a tree of parts, a car, an engine, its wheels, so forth. And the visitor is often used in conjunction with you're traversing a tree of heterogeneous objects, and that's sort of the point. The objects are different, so you want to do different stuff with each of them, but you're going to traverse this tree. That's not really the traversal itself isn't the point of the pattern. If you just needed to traverse a tree, we have another pattern. It's called recursion that all languages support pretty much anymore. But the key is the double dispatch. You have a tree of nodes, and they're heterogeneous, and then you have different operations that you want to perform on that tree of nodes. So the example of an abstract syntax tree, you have all the nodes representing all the different constructs in your language, and then you have a visitor that wants to pretty print them, or compile them, or whatever. And the operation you want to perform at each node is a function of both what the node is and the thing that's traversing the node. So I'm going to leave the traversal out in this example and just focus on the double dispatch. So I'm going to review just a little bit of Java, just make sure we're all on the same page. So this is normal polymorphic dispatch in Java, right? You have an interface, priceable. Books, CDs, and DVDs are all priceable, which means that they have this method price that stupidly uses a double to represent money. And so now you can get a random priceable. All the compiler knows and the runtime is that this thing is priceable, and therefore we can call this method. So this would be the same in any singly dispatched object-oriented language. Python, we take out the type declarations, Smalltalk, whatever, but the basic notion is the same. So the polymorphism is the poly, many, morph shape. The many shapes are these elided bits of code, different depending on what kind of thing this is. This is non-polymorphic dispatching, just to make sure that we're clear. This is just overloading, right? The method happens to have the same name because Java lets us do that, and the type determines, is really part of the name. So if you get a random object, and all the compiler knows is that it's a Java-lang object, and you call display O, this will print object. And if you try and cast it to a book, it'll either print book because you've statically said this is I want this one, or the cast will of course fail. So this is really the same as if we had just named these methods differently. They're just different methods that Java lets us pun and have the same name. Objective-C, for instance, does not let you do that. Okay, so this is hand-coded dispatching. And the reason you would want to do something like this is because if you didn't so before priceable was part of the objects, but displaying for whatever architectural reasons, we don't want to add a display method to the object itself. The objects may exist, someone else wrote them, and we just need to display them for our application, so it's not part of the class itself. Interestingly, in Smalltalk, you could just add the methods to the object that already exists, and would obviate even this use of the visitor pattern. So we're sort of adding functionality to these objects from outside. So since this doesn't work polymorphically or at runtime, you could write hand-coded dispatching where you just have one method display object and then use runtime type information to figure out is it a book or a CD or a DVD and then do the appropriate thing. Of course, that kind of code is exactly what we were trying to avoid when we invented object orientation in the first place, right? You don't want all these stupid if statements because if you add a new kind of thing, you got to add a new clause to every switch statement like that in your code. So visitor is designed to solve that problem by providing double dispatch. The display operation that gets chosen will be a function of both what's being displayed and how we're displaying it. So the way you implement this in Java is you define an interface that has a separate method for each kind of thing that you want to display. And then also, you do have to touch the objects that are going to be visited, but only in one way. And you can support multiple visitors with this one. Add a method display on where the object, we'll see in a sec, the displayable will be like a book. If you ask it to display on a particular display, it calls back on the display. Well, we'll see what it does. Let's skip that. Okay, so here's the two the implementations of a display, a graphic display and a text display. They presumably do different things. Put pictures on the screen, put text on a web page, whatever. And then here's the things that are actually displayable. So they don't have to know anything about the two kinds of display, graphical or textual. But when they are asked to display themselves on a particular display, they provide the information of what they are. They turn around and tell the display, I'm a book, essentially, right? This display book could just be called I'm a book, and it passes itself. And the thing that's really annoying, well, it's shown here because we use different names. You have to implement this method in every class. You can't inherit it because the whole point is you're specifying, right? So you guys all get this. So at last, we can actually use this. We can get a random displayable, a random displayer, and then use the double dispatch to get a graphical or textual display of a book, a CD, or a DVD. Oh no, we want to add some new classes. So paperback book, hardback book, they're both kinds of book. How should they be displayed? We could just use the existing display book. Unfortunately now, they're all going to be displayed the same, and if you have some application where you need to display paperbacks and hardbacks differently, you're either screwed or you have to go into the implementation and all of your visitors and now put in another stupid switch statement, instance of paperback book, do this, whatever. So we could also add these new methods, paperback, into the display interface, or sorry, the visitor interface. So we add them there. We go back to our display helper, which I sort of skipped over before, add the new methods. And then this is an interesting point. In the display helper, which is sort of an abstract base class for the actual displays, we can imitate Java's inheritance by saying the default thing to do for either of these subclasses of book is just to call the book method. So if our existing displays would need to be recompiled, but then they would pick up this default behavior. And if you had a particular one, in say the graphical one, you wanted to display paperback specially in some way, you could then provide a new method for paperback but leave the hardback book alone. But the thing that's a little goofy about this is we're re-implementing inheritance, right? When we just have single dispatch, it just works. When we want double dispatch, we have to sort of roll our own thing. So then this cool Java kids these days, oops, yeah, so the cool Java kids say, all right, well this is stupid, let's use reflection. And now we really get into rolling your own, and the Lispers in the audience will appreciate compute effective method. This is essentially what Lisp has built in. But this happens, basically what happens is when you say dispatch on some object, we use reflection to look at all of the methods that are available on the display, graphical or textual display, pick the one that's the most appropriate, and then invoke it, again, using reflection. And so all the guts are in compute effective method, which is the next up. And this is a mess. But that's Java. So we try all the superclasses, walk up the tree, thank God Java only has single inheritance. But of course then we have interfaces, and so then it's just like, well, what do we do? We'll just take the first one that matches. I don't know if that's right, but whatever. And so now it's a little different than how single dispatch might work. I guess that wouldn't matter. They would just collapse. But we'll just pretend that doesn't matter. And then, I'm sorry, what's that?
All the methods belong to classes, so you should just be able to walk up.
No, this is what we're looking for is we're looking for a method called apply for, and we're looking at the type of the argument. So if I'm and this is sort of more generic than the display thing. If it may be the case that I have a visitor that implements a apply for foo, where foo is an interface. And if I pass it an object that implements foo, I want it to find that method. So I got to look for those methods. And so this now, we can use this dispatch helper, which was pretty generic, to implement display. So now we just have one method called display that takes any kind of object and uses that dispatch method that we just looked at, which uses reflection to find one of these four methods and display it. Now the nice thing actually about the reflection-based thing, which is of course the nice thing about Lisp where it's built in, is that you can now essentially add methods to classes that, final classes, right? We can say, here's how you display a string. And there's no way you can do that, even if you had the source code. Well, I guess if you're Sun and you have the source code, you could add it, but no one else can. So now we can say display foo. So that's an advantage over the non-reflection based implementation of the visitor. The problem is that we had to write all this stupid reflection code. So so that's Java, intended to look like a nightmare. But I think I was pretty fair to it. So in Common Lisp, one of Common Lisp's many fantastic features is the notion of generic functions. So the root of all object orientation was Simula, right? We all know that. Alan Kay took Simula and Lisp, mixed well, produced Smalltalk. So that was the path of goodness and light. Barney Sturstrup took Smalltalk, static, bondage and discipline language, mixed with C, another relatively static language, and produced C++. That was the path of darkness. And since then, of course, since the tree of languages isn't really a tree because you can cross back, the Smalltalk branch has gone off, and then Smalltalk begat Objective-C, right, which was, so you take Smalltalk and then C, mix, and you get Objective-C. Java took a bunch of stuff from Objective-C, and so we're moving, but obviously was syntactically and in other ways tied to the C++ dark path. But it's sort of moving over here, and then languages like Python and Ruby and Perl, to the extent you consider it OO, sort of are all pretty much in the dynamically typed Smalltalk school of the path of the light. So basically, all of the good stuff in object orientation actually came from Lisp originally anyway, plus Alan Kay. And what Alan Kay added was this notion of message sending. And the Lisp guys at the time that Alan Kay was doing his work were thinking, okay, well, we should be able to add this back into Lisp because Lisp is the ultimate programmable programming language. And so initially they were like scrapping around trying to get copies of Alan's papers early, in the early days in the 70s. And so they sort of had to invent a bunch of this stuff themselves because they couldn't get the papers. They had a very message sending, single dispatch oriented. There was a special function send, and you said send the name of the message, method name, whatever, and the arguments, and the object to send the message to, and then any arguments, and it would be just like Smalltalk. But then they said, well, that's silly, we can generalize that. And so by the time Common Lisp came around, there were a few ideas that were combined into the Common Lisp object system class that generalized from single dispatch into multiple dispatch, where you define a function that takes any number of arguments, and you can dispatch on any of the arguments any of the required arguments that it takes. Now, the one weird thing about that for people who are used to thinking in single dispatch languages is that methods don't really belong to classes anymore. We've sort of gotten away from the notion that here's a class is some data and the operations that operate on that data. Now you define classes as essentially data, and you define generic functions, which are functions that could, in theory, be applied to anything, and then you define methods that are attached to those generic functions and provide specific implementations, sort of like that reflection-based dispatch did, except it's all just built into the language. You get true multiple dispatch. You get also, the big advantage is that it works, there's only the one mechanism. So the way inheritance works for single dispatch is exactly how it works for double dispatch. Common Lisp also has multiple inheritance, and how that is all sorted out is the same and well-defined and really actually not that hard to understand. There's some other, and then once that generalization was created, that allowed all kinds of other fancy things, like you can have sort of parts of methods. You can have a main method for a particular class, and then you can define methods that run before the main method and after the main method and around the main method. And when you actually invoke a generic function, all of these applicable methods are taken, sorted out, and combined to produce the actual code that runs in a much more, it's not just picking one thing to do the way single dispatch does. So get all the details, read the book, chapters 23 and 24 or something. So back to, here's how it looks in Java, here's how it looks in Lisp. So this is, here's the classes, I've elided the definition of the slots, and then we define a generic function, price. We can price anything. Book, CD, so this is the actual parameter name, this is the class name, and we're just specializing on one argument. We can also, as we could with the reflection one, we can specialize methods on numbers and strings, any type that exists in the language, they're all classes. Now double dispatch, instead of writing reams of code, we just write this. We have two ways we want to display stuff, graphic display, text display. Now display takes two arguments, and we specialize the things we want to display and the things we want to display them on. We can organize the methods in a different way. And that's another question everyone's asked, like, okay, so if methods don't belong to classes, where do they go? And there's no good answer. It sort of depends. If you're, some generic functions are really generic, could be applied to anything, but all of the implementations are sort of cohesive. So put the generic function and all of the method definitions with it. Other times the methods really do belong to the classes conceptually, intellectually, and you put them with the class definitions. Lisp doesn't really care. So triple dispatch, quadruple, whatever, in the back.
So what happens when there's two equally applicable methods?
So the question was, what happens when there's two equally applicable methods? There's a canonical algorithm for sorting the inheritance. So like, basically, the first level of decision is, by default, it's left to right. So if you can decide left to right, you're done. Though when you define the generic function, you can actually specify a different order if you want, which is rarely useful. But there's one case where it is very useful. And then if there's actually what seems to be an ambiguity, then there's basically an algorithm that you can understand, which is, take the class hierarchy and sort the methods according to this partial ordering and pick, and then they're.
Is there a standard algorithm for catching missed cases or
For catching this.
catching missed, like, suppose you don't have a display for like anything
Right.
method up there.
You can, right, you can. And in fact, if you don't specialize, like if I just had, R here with no parens and no class name, then that's implicitly specialized on T, which is the top of the type lattice.
Okay, what if I didn't really want to, I just wanted not to miss it, I'm just trying to get everything down. Is there a way of catching that, or?
Not statically.
Okay.
You can use the sort of reflective capabilities of the meta-object protocol to find them, or you can just put in a default one that signals an error, but there's no static. It's not a B&D language, so it's like no, because you can define the method at runtime. So there's no real way to answer that question. Okay, so that's generic dispatch. The next topic I want to talk about, now for something completely different, is to look at how different languages handle error handling. And again, I'm just going to briefly set up what is error handling. I'm sure we all, not because I don't think you know, but because I think we all have our own slightly different ideas. So I'll just let you know what mine is, and then we can at least accept it for the next 16 minutes. And the reason I want to talk about this is because it's an example of how sort of back to the Narian notion of a theory of the program. Well, the theory of the program can be more or less simple, partly determined by the constructs that we have available to shape our program. And error handling is a particular one that it's hard to get right. People confuse themselves in many different ways about it, and many languages do a lot to help you get confused. So the way I like to look at error handling is by starting from the notion of invariance, which I'm sure you're all familiar with. Dijkstra taught us this. Bertrand Meyer built it into Eiffel, the notion of preconditions, postconditions, class invariance. And whether you think of them explicitly, the way Dijkstra encourages us to, and the way Eiffel sort of pretty much forces you to, every function that you write, and I'll focus on functions rather than class invariance, every function has a precondition, right? The stuff that has to be true for this function to possibly work. And every function has a postcondition, which is the stuff that will be true if the function succeeds. And many people program very informally, but that's what you're thinking about when you're thinking about what does my code do. I further split that up, the precondition part, into the actual precondition, which is everything that has to be true. Right? If you have a function that opens a file, reads it, and parses it, one of the things that has to be true is that the file has to exist. Which doesn't mean your program is going to crash if it doesn't exist, but the function will not succeed if the file that it needs to open is not on the disk. The formal precondition is what folks like Meyer and Dijkstra like to focus on, which is the subset of the actual precondition that we can prove by logic, or that the caller could meaningfully check. But the existence of a file, you certainly can't prove by the logic of static analysis of the text of your program that that file will exist. And you can't even really check it in the caller, because you could check that the file exists, go to call the function, and someone deletes the file, and it still doesn't exist. So there is this gap between the actual and the formal. And that gap is where error handling comes in. So when I talk about error handling, I'm talking about Murphy's Law, stuff. You have to deal with this stuff. It's not that there's a bug in your program, and it's not that there's nothing you can fix in your program, but if you don't deal with it, the guy who calls the function that's supposed to open the file and return some results based on the contents of the file, well, the guy who called it is screwed if the file doesn't exist, and that guy can't succeed. And if you just continue as if everything was fine, now your program has a bug. So if to break it down, if the formal precondition isn't satisfied, game over. Like that's a bug. If If the formal and the actual are satisfied and the function doesn't satisfy its postcondition, that's a bug, and you can just fix that. There's no excuse for that. But this interesting gap is when the formal precondition is satisfied, the caller did everything right, there's no bug in the function, but reality is the actual precondition hasn't been satisfied, and so we can't carry on. So now you can be defensive and try and make your preconditions looser and define, well, this is what I'll do if such and such bad case happens, and I'll deal with these corner cases. But ultimately, you cannot account for every possible corner case, and better is to just handle errors properly, by which I mean you should fail cleanly if your formal precondition was satisfied and you can't satisfy your postcondition, which means something in the actual precondition wasn't satisfied. And you have to detect and deal appropriately with the lower level failures. You call a function and it fails, you can't pretend that everything is okay. So, how do different languages deal with this? Well, we all know the C style, right? Every function that could possibly fail returns some distinguished value that the caller is responsible for checking, and then everyone forgets to check, and thus underlying failures are completely ignored, and 20 million CPU cycles later, memory is totally corrupted, and we all wonder what went wrong. So Java and Python came along, and many other languages, C++, and said, okay, well, that's just insanity. So what we need is exceptions where at least the caller is now, if they don't do anything, the exception will continue propagating, and you will sort of satisfy the base requirement of if you call something that fails and you can't recover, you have to fail. Exceptions provide that, right? You either catch the exception and patch up the world, or you don't, and then you fail because the exception continues to propagate. So that seems fine, and when you combine it with try finally, you actually have a chance to clean up as the stack unwinds. Life is pretty okay. But the reality is, anyone who's worked on big systems in these languages knows, is that you almost never can recover. Because down at the bottom, something goes wrong. And by the time you get to the level of the program that would actually know what the right thing to do in the context of this application, it's too late, because you've unwound the stack and lost all of the state, and you have operations that were half done that either are too expensive to redo or can't be, like if you're lucky, you cleaned up with try finally on the way up, but now you got to redo the whole computation. So Common Lisp provides what I think is a much nicer method for dealing with errors, which is they split instead of a two-part, traditional exceptions are two-part. Down at the bottom, you signal the exception. Up at the top, somewhere above, you handle it. So signal, handle. In Common Lisp, there's signal, but don't unwind the stack. Let the signal go up the stack. Someone up here can say, I know how to handle that, and then the way they handle it is there's a third part, which is a restart, which can be established anywhere between where the condition was signaled and where the handler is set up, or actually even above, that says you can unwind to the restart, and then the restart will run and do some code. So I'll look at an example of how that actually works. So here's an example call chain. So imagine we have an application that's a log analyzer. I can't really read this, but this says log analyzer. So that's the top level function. This could be a command line utility that analyzes a bunch of log files. It uses a function analyze log to analyze a single log file. So this guy's presumably going to take a log file, digest it in some way, and return some results, and this guy's going to aggregate all the results. Analyze log then, in turn, uses a lower level function parse log file that knows how to parse some particular kind of file, but one file. And parse log file uses the function parse log entry to parse each individual entry. So this guy's going to call this some handful of times. This guy's going to call this probably once. And then this guy's going to call this however many times, millions of times for each line or entry in the log file. And so there's a lot of state, right? If we're down here, and this is where things are going to fail, right? You're going to get to one line in the log file that's malformed, and this guy's going to say, I know this is malformed because my whole job is to parse these things. But it's not this guy's job to decide what to do. Maybe that's a fatal error, and we need to just quit the program, page the sysadmin, whatever. Or maybe we just skip it. It's okay. Or maybe we apply some heuristic and parse it, a little bit sloppily because this log maybe came from a little spacey source. But it's not his job to decide. So in Java, this guy would say, well, crap, this is malformed. I'll throw a malformed log entry exception, and he'll go up here. And this guy, by the same token, it's not really his job to decide what to do. So he's like, well, I could catch it, but I wouldn't know what to do if I did, so I'll just propagate it. And so now, this guy was in the middle of a 1,000,000-line log file when he got this malformed log entry exception. He's passed it out. Now we've lost where we were in the log file. This guy doesn't know what to do because he's still a helper function. And so he passes it. He was in the middle of the 100 log files that we're passing. And so he throws out to here and has lost track of what file he was on. Well, you might know, but. And now this guy is the top level application. He knows what the policy is for this particular application, but now it's too late because we've lost all the state. So in Lisp, like I said, oops. Instead, this guy signals a condition. The stack doesn't unwind. Conceptually, the condition goes up the stack. Really what happens is we kept a little basket of who knows how to handle what kinds of conditions as we went down. So we find the right guy, but at the same time as he signals this condition, he can also say, I have a couple strategies that I could use. I could skip this entry. You could give me a new string to parse in the place of the line that I found to be malformed, but I certainly don't know how to use that. Or I had this other heuristic parse, and I could use that if you want. Likewise, actually the skip entry really belongs here. But so these two guys both set up some restarts and say, here's how we could proceed if it's okay with you. And so then this guy, so we're in Java, he would have the top level exception handler that would in Java, catch the exception and say, crap, I don't know what to, I lost all the state, so I'll just quit and page the system in anyway. In Lisp, he would establish a condition handler that says, okay, if you get the malformed log entry error, then look to see if there's a skip entry restart. And basically, he's sort of looking back up the stack. And he'll say, oh, parse log file has a skip entry restart. I'll invoke that restart. And then this guy will he'll have a little bit of code that says, well, here's how you skip an entry and move on to the next one, and everything just proceeds. So that's basically, there's, and that facility is typically used for error handling, but can also be used for any kind of other, communication up and down the stack. You can signal warnings in Lisp that the default behavior is to print a message to standard out, but you can catch the warning and muffle it with there's always a muffled restart warning, and you just say, I don't want to print that.
So, good question about this. What is the benefit of this scheme over, for example, having log analyzer and instantiate analyze log, which is data to parse the log file, each saying this is what I would like you to do in response to an error?
Right. It's in a way, it's just a mechanism for doing that easily. You basically could, particularly in Lisp where you have first-class functions, you could have all of these functions take an argument which is a function, which is here's what you do when you can't parse the entry. The real problem with that is that this guy, so this guy can know about this, the top level application probably knows who's going to be doing the parsing. The problem is this guy doesn't really care about that. So you basically, sort of the same reason as you use exceptions, right? All the intermediate guys don't want to have to know, and even say this huge list. Essentially it's providing a back channel for passing down those special handlers.
So you're basically saying that if we don't currently program in common Lisp, we won't think of this programming burden?
Well, you could, but I didn't even try. You could implement a mechanism for doing this in Java, right?
I don't know. The message is that if we don't program, if we just know common Lisp, we won't be able to use the patterns there, but if we actually do program in common Lisp, we will be able to use them.
That's at least the strong implication. So I used to be a hotshot Java programmer, and you could use thread local variables and appropriate use of try finally and catch and concepts and special exceptions and throw them to basically emulate this the same way I use the visitor pattern to emulate the double dispatch that's built into Common Lisp. The problem is, and this actually really gets me to my next and final point, which I'm going to have to boogie through, which is the real winner feature of Common Lisp is, I'm sure you've heard someone talk about it, if you've heard anyone talk about Lisp, is macros. And these are not your father's C preprocessor macros, right? These are the language parser parses into a completely generic abstract syntax tree, and you can hook into the compiler your own little code generator at any scale you want, from a tiny little, let's see, let's skip that for a second. So in Lisp, the if expression is sort of primitive. There's the condition, and then there's a single then and a single else expression, which means that if you want to do two things in one branch, you got to use this other ugly thing called prog-n to say, so if some predicate, do these two things. Well, that's not terrible, but it sort of sucks. So we can write a when macro, except that this one happens to be built into Common Lisp. But this is a tiny little compiler that says if you see an expression of the form when, a condition, and then any number of following expressions, transform this into the if expression on the previous page. And the reason that this is important is because both the generic functions and the condition handling system that I just showed you, if they didn't exist in Common Lisp, you could add them yourself with exactly the same syntax that they are provided, that is used to provide them in Common Lisp. In Java, you have all of the underlying machine. I mean, it's a Turing complete language. And it's even beyond that. It's got thread local variables. It's got exceptions. You could duct tape together an equivalent of the condition system in Java, but you could never hide it because you have no way of abstracting the syntax. And so that's where macros really, it's hard to explain macros because trivial examples like this, you're like, yeah, whatever, that's trivial by definition. Big examples are sort of too hard to wrap your head around in the 22 seconds I have left, but I'll try. So here's a medium-sized macro. So def test, and this is from my book, more or less. So this is a def test. This is, def fun defines a function. So the idea here is I just want to define a function that does like a unit test. So this is all I want to say, right? This def test, its name is foo. I want to check one thing, which is that 1 plus 1 is 2. So I'm unit test for my addition function. This is what that macro expands to, which is a little hairy, but you can sort of, you could write this by hand every time. It wouldn't be terrible. A little gross, but you can imagine that. The problem is that the check is also a macro. And so that's doing this. And there's one nice thing, is that it can use the expression equals 2 plus 1, 1 as both a thing to run when you run the test and also as data, a label that I'll print out. So when the unit test prints, and I didn't have to type it twice and risk typing it wrong one place and getting these completely confusing printouts from my unit test framework. And the other thing is that with test results, here is doing really a ton of bookkeeping for me. So this is the full expansion. And this is why it's hard to explain macros, because as soon as you show this slide, everyone's like, okay, this is terrible, I don't want to think about this. But this is what's, none of this is actually really hard. It's using the condition system to signal passes and fails, and I keep track of all the passes and fails, and I print them out. It's all the stuff you would do. And you could abstract it a little bit differently. Obviously, Java test frameworks don't actually require you to write code like this. But the fact that I was able to go from that def test form, and I can write, a gazillion of those, and get, all that is powerful. Back just briefly to the if-when example. So you can add these little tiny control constructs. Well, how long would it take to do that in another language? Oops, where did it go? Well, Java added a little for each statement in 1.5. The JSR for that ballot started in December 2002. The final release was September 2004, 22 months plus however many years you have to wait before you're allowed to drop support for 1.1, 1.2, 1.3, and 1.4 versions of Java.
What's the difference between a macro and just a function?
So the real difference is that macros run at compile time, which is, unfortunately, due to other characteristics of this, a little bit of a fuzzy thing to say. But you can take, when well, this one doesn't really, so actually, let me show you. This slide doesn't really demonstrate, but so here's a macro language that is also discussed in my book for generating HTML. And the macro, which runs when I compile my Lisp program, turns an expression like this. Well, it doesn't actually return this, but it turns into code that just says print this, right? I could, function could take this data at runtime and figure out that it's supposed to print, a p tag and then this string and then another p tag. But that would be the actual code that would run at runtime would be doing all of that thinking about, okay, what tag is it? But the compiled version is just, the equivalent of println this text.
So a macro is mostly a performance thing?
No. Well, the other difference is that you can use arbitrary syntax. Which actually the earlier example shows pretty well. Well, here's a better example. So these are uses of a macro to define a parser that's sort of like a yap kind of thing. Don't worry about the exact language of this grammar, but this def prod is a macro, and this plus is not. The other difference besides the optimization that you can get, which is substantial, is that you can use arbitrary syntax that doesn't have to be. I guess in the end you could have any function you wanted and pass it quoted data and let it essentially interpret it at runtime. But then your code, the code that invokes that special syntax doesn't look like, right? It's the two flaws. It's going to get interpreted at runtime, which could be very expensive. So the really big scale macros. This doesn't do anything except for squirrel away a bunch of information about the grammar that this production rule defines until I get down here and say def parser arithmetic expression, and then it looks up the transitive closure of expressions that are used and compiles that all down to a single function that implements the parser. And then I can turn around and use that parser, def parser arithmetic, to find a function arithmetic, which can now parse a string, and I can use that. So, the super functional programming guys, Haskell and MLers and stuff, will say, yeah, I can do all this with higher order functions. And you sort of can, but sometimes what you want to abstract is the syntax. It's not the functionality. Functions are good for abstracting functionality, but sometimes you just want to be able to write very concisely. One last thing I just want to show out. Here's another one. This is also from my book. I write a parser in my book for ID3 tags. And this is essentially an SExpress version of text straight out of the ID3 spec. And this turns into class definition and method definitions and how to read and write an ID3 tag. And obviously I just defined some other things in the same way, but essentially I just took the spec, put parentheses around it, and it gets compiled into code that knows how to parse these binary files. And you could, and so the point I want to just be able to write that. I don't want to have to write higher order functions or think about the world in those terms. I just want to say, this is what I want to say, and then macros let me have what I say mean what I want. So I think I'm running well over time. Rob's going to give me the hook.
Yeah, so I guess that's the end. Should we take one more question? Any other questions?
It's clear looking at the syntactic and semantic
expressive power of Common Lisp that a single program can create a lot of functionality, a lot of power in very little code. Can you talk to, at least briefly, like the kind of the flip side to that double-edged sword, which is readability? If you have lots of programmers with a large code base, I mean, any symbol in the program can mean just about anything, and change the functionality of the program, the behavior of the program in pretty fundamental ways, from a pretty local level. So, are there very large-scale projects written in Common Lisp across like a large number of developers?
Sure. So there's a couple answers to that question, and it's a common question. In some ways, the simplest answer is, look, macros are a way of creating abstractions. Functions are a way of creating abstractions. We don't look at C and look at libc and say, okay, well, look, here's all these standard functions. But wait a sec, C lets us define new functions. What happens if everyone writes their own version of strcat or whatever? And the reason we don't worry about that is because that would be insane, right? You're supposed to use the ability to write functions in C to create new abstractions, not to create your own little private weird language. Likewise, macros. People tend to get beat up pretty badly when they use macros. I mean, just the way, like you've all seen the C preprocessor macros that let you write Pascal in C. If you do that in Lisp, it's the same bad idea. So it's just a way of creating abstractions. They don't let you change the global meaning of a file, or of a program. I mean, it's contained. So it may be the case that when you see, define binary class, you don't know what that means just from looking at it. But when you see in C, foo, open paren stuff, you don't know what that means either. Either there's documentation, or you look at the source code, or it's well named and it's pretty apparent more or less what it does. So it's really the same problem. How do you write? And I think it's actually a better solution in the sense that it is the macro encapsulates a pattern. Like the alternative is you have, so to implement the ID3 parser, there's, a dozen different constructs in the spec that you have to implement. So I have a defined binary class for each of them. If I didn't have macros, there's a bunch of code I have to write. I have to define a class, I have to define a read method, I have to define a write method, and that code all follows a very particular pattern. But if I wrote them all by hand, there'd be one that would be a little different. And someone comes along and looks at my code and he's like, oh, that one doesn't follow, first of all, they have to recognize the pattern. So having recognized the pattern and put that into their theory of the program, then they look at the one that's different and they say, okay, is that different because some subtle reason that's totally escaping me? Or is that different because that's the right way and all the other ones are wrong? I mean, you have no way of knowing. Whereas if you have a macro, you're basically putting a stake in the ground and saying, this is the pattern. I've implemented the pattern. I've automated how the pattern should be done in the sort of coding pattern sense, of the Alexandrian pattern. And now it's possible there's a bug in the macro, or it's also possible that someone misunderstands how the macro is to be used and there's a bug in the use of the macro, but at least there's not this sort of slippage of code, it's different, but who knows why. So it actually makes it more expressive of your intent and therefore easier to understand when used well, right? Like, it is a powerful tool and people, if you're gonna be stupid about it, like there's no help for that. But, I worked at WebLogic in the early days and we had exceedingly good Java developers for the most part, and Java is a very bondage and discipline language. It's supposed to make it easy for big teams to work together, and we still had code that was terrible, that nobody could understand, and there was no help for it. Like I said, I think your defense on incomprehensible code is, exactly Google's policy of hiring good developers. And
why do you suppose it's not more popular? Like, why don't we all write it?
right. We have time for this? So yes, this is really, probably where I should have started. Actually, I have some notes.
Do you know of any big applications written in Lisp other than Emacs?
Other than what, Emacs?
Emacs.
Well, so there's, okay, so the big success stories at the moment, and some of them are getting a little aged, but so we all know Paul Graham wrote ViaWeb and Common Lisp, sold it to Yahoo for $40 million. Of course, that was in the boom time. So, but he beat out his competitors. Naughty Dog Software used Common Lisp to basically implement a compiler for the PS2 and implement a Jackson Daxter in that Lispy language. whose compilers were in common Lisp. Sort of probably the big projects were done, sadly, in the 80s, where the symbolic Lisp machine was Lisp from the chips up. So they wrote a whole operating system. I don't know how many developers they had working on it, but it was orders of, and part of the thing with Lisp is you tend to get more done with fewer developers, so there aren't a lot of 200 developer projects out there, but a 10 or 20 person team develops a whole operating system from the chips up using Lisp. I don't know how many lines of code it was, but that's not trivial, including a C compiler. You could run a C compiler on this machine. They had a C compiler, they had an Emacs, they had networking stacks to talk to pretty much everything. They had a file system that could interact with every file system on the planet at the time. Those are non-trivial programming tasks.
One big one is ITA software, right?
Right, Orbit's right. The website for fair matching is largely written in Common Lisp, the pattern matching algorithms. But the question, so why doesn't everyone use it? So there's three approaches to that, or four. There's three wrong ones and one right one. So some people like to come along and say, well, there must be something intrinsically wrong with the language. You can just fix some technical thing, get rid of the parentheses, or do this, or do that, and somehow that will fix the popularity problem. I think that's not the answer, particularly because Lisp is the ultimately malleable language. There's almost nothing that you could want from the language that you couldn't implement in userland if you wanted. So the fact that things are the way they are is due to for the most part, that's how they ought to be. They're little rough edges, and it was standardized, and no one wants to reopen the ANSI standard. So it's not a technical problem, I don't think. It helped, popularity of Java is helped by the fact that Sun poured money into Java and Java implementation technology, and but Python and Ruby didn't have that kind of money, and they managed to sort of pick up steam. And they're still, Python is slow, but people use it because chips are fast now.